The three objectives for acceleration in section 2.2 are to describe motion when the velocity changes. In the real world, your velocity is not really constant for the most part. You have acceleration. When you drive a car, what do you do when you hit the gas? You accelerate. When you hit the brake, you decelerate. You always have acceleration around you. Part 2, compare graphical representations. So like we did yesterday, we're going to plot different things along the axis today though. And third, we're going to apply what are called our kinematic equations, which might be one of the most important things you learn in all of physics, the kinematic equations. You're going to use them over and over again in every field. Okay? Let's take a look at this. Now, acceleration. Acceleration is defined as the rate at which velocity changes over time. So take a look at the formula, please. It should be very straightforward based on the definition. What does delta V mean? Change in velocity. Delta T? And what is the definition? The rate at which the velocity changes over time. Over means divided by time. So our definition of acceleration clearly is analogous to the formula given. Agreed? Okay? Now, look at your dimensions. What are the units of velocity given in? And what are the units of time? So it's meters per second, right? Meters per second, which is just meters per second squared. That's what I'm showing you on the board there. Okay, again, the units of velocity are meters per second. Here's what it looks like really, okay? Looks like this. Meters per second divided by second. Right? That's what I'm seeing here with the units. Well, when you divide, it's the same as multiplying by the what? So this is really meters per second times 1 over seconds, which is meters per second squared.
How would that...
James, there's your hand.
So that's like, when you're doing that, you're basically just saying like how much velocity in this case is gained in a certain amount of time.
Absolutely right. That's exactly right. Acceleration is saying, say it one more time louder, James.
How much velocity is gained in a certain amount of time?
Gained or lost, like in a certain amount of time. So in this case, we're talking about you're gaining a meter per second in velocity every second. If the answer was 7, it means you're gaining 7 meters per second in velocity every single second. Let's think about this hypothetically, okay? You're in your car, and you're driving at 20 miles an hour, but you're about to enter onto a highway. And you start accelerating at 9 miles per hour squared, in a sense. Miles per hour. Okay? What that means is that you would technically gain 9 miles an hour in your velocity in a duration of 1 hour. That's a very low acceleration, right? So you might be accelerating at like 10 miles an hour every 2 seconds. So that would be 10 miles per hour per 2 seconds. Now that's going to be even more complicated, but the idea is the same. It's how much are you accelerating in a given time period, or how much are you changing your velocity in a given time period.
So how would deceleration work?
It'd be a negative value. You'd be losing velocity, right? How do you decelerate? You hit the brake. You lose velocity, okay? It goes down. James?
Is there any differentiation made between acceleration in terms of velocity and speed? Or?
Acceleration is always the change in velocity. Always. It's never going to be speed. Okay? So this is why we're talking about velocity, and even though we were using them interchangeably. The acceleration will always use velocity. Will never use speed. Okay? Will never use speed. Alright. With that said, let's take a look, please. Okay? Go ahead, list your givens, list your desired variable, list the equation you're going to use, attempt to isolate, and solve. Okay? So we're going on to the next example now. Come on, I shouldn't see people loading notability. That means you were doing something else. It should be loaded already. Nothing else should be up. Free pass. First time. Nobody else. That's it. James got lucky. It happened to me the other day, so I kind of feel bad. So I'll let it go for today. Every time I do it, I give one freebie in my classes. There it is. It's the truth, though. I do it sometimes.
So in this formula, we have, negative 1.8 meters per second.
Mhm.
What do we do with the original, where we put that in terms of this?
What do you mean the original?
Like 9 meters per second.
Okay, that's what we have to talk about now.
It's not velocity. That's velocity.
Which velocity is it?
It's
Initial or final? What's the final velocity?
negative 9.
No, it's because it's 9 to 0 and you subtract it, so
Oh,
it is
it's a
the
complete-
change.
oh.
It happens to be, but let's list VI and VF just for now. You're right, though. You're absolutely right. So it is the initial velocity. That's what that is, right? It's moving at 9 meters per second. But then what happens? It goes to a complete stop. What is that velocity when you stop?
0.
So your final velocity turns out to be 0. So what Nick was saying, Lou was saying, what Lou was saying was, I swear one of these days I will, was that you're going to have here a delta V value, okay, a change in velocity of 9 in the end, really, okay, of 9. But let's list them as initial and final when they're given like that. So what's our definition of acceleration? What's our definition of acceleration, formula-wise, from the last slide? What do we got? What do we got here?
A equals delta V over delta T.
Good. So we start with that formula, right? What are we looking for in that formula?
Delta
T.
T, delta T or T, either one, okay? So we're trying to find time. Do we have to do anything with the units, or are the units good? Units look good to me. I see meters and I see seconds. It looks like they're consistent, right? As long as they're all the same, we're good to go. If it had been kilometers per hour and the acceleration had been kilometers per hour squared, you're also good to go. Okay? But your time answer would have been in hours then in that problem, but now it's going to be in seconds. All right, rearrange the formula on the upper right part of the screen, please, on your own. Rearrange it. Solve it for t, please. Now here's where it's important not to drop the delta where you see the v, right? Why do we not want to drop that delta right away? But with the v, we don't want to, because it's really, remember, the change in velocity? The change in velocity?
What's the change in velocity?
So, you want to think about what your initial velocity is and what your final velocity is.
Oh, so you subtract.
So we're going to have to think about that for a second, how we're going to do that, yeah. What do you get when you solve for t, though, generically? Solve for t, t equals what? What's the expression look like? Not with numbers, just variables.
Delta V over A.
Good, delta v over a. What did you do, Gio?
Multiply by delta T on both sides.
Good, and then?
Divided by A.
Yeah, so technically what did Gio do? He switched these two. Okay? He flipped those two around. That's what he did. Agreed? Okay. Now, change in velocity. What is our definition of change in velocity?
Final velocity minus initial.
Very good. Final velocity minus initial. And it's important that we have the right order there. And you'll see why in a moment.
We would get a negative.
Yeah, very good. You get a negative time, which you can't. Take a look. In this problem right now, we're good to go because the acceleration was negative, but the VF minus VI is going to be 0 minus 9. It's also going to be negative. Two negatives make a positive. So again, plug in here, please. Plug in your numbers now.
Wait, is always final minus initial?
Yeah, always final minus initial. Okay? Always finest minus initial. I'm going to move up a little bit further. I know some of you are still writing. Okay? So we plug in for final velocity is 0. Initial velocity is 9. 0 minus 9 is negative 9 over negative 1.8. The meters cancel. One of the second units cancels, leaving behind seconds for time. What do I get? What do I get? What is it?
5.
Units?
Seconds.
Good.
Wait, I'm confused. You have 2. And how do you get the seconds again?
Okay, so let's take a look. The numerator becomes negative 9, right? Meters per second. The denominator is negative 1.8 meters per second squared. So meters, meters, seconds, drop off one of the seconds, leaving seconds in the denominator of the denominator, which bumps it up to the Numerator.
What if it was just seconds in the numerator?
In the numerator of the denominator or just the numerator? What do you mean? You said what if it was just seconds in the numerator?
No, you said it's seconds is the denominator of the denominator.
Would it have been here, you're saying?
Yeah, or like up in the.
If it were here,
Yeah.
it remains in the denominator of the unit. So this would be 1 over seconds. If it were here. If it were here, it also goes down here. If we're up here, it stays up top.
Okay.
Just mathematical rules. You've seen these before. It's just a matter of recollection. If you have something in this location, it's really in the overall denominator of the answer. It would go in the denominator, so it'd be 1 over. This is in the numerator of the numerator, which leaves it in the numerator. Denominator of denominator is also in the numerator. Numerator of the denominator is in the denominator. It's like when they're opposites, they stay in the denominator. Let me show you what I'm saying, because I know that was a lot of words all at once. If you have units, and let's say you have a final answer of 1 over seconds over 1 over meters. Okay, those are the units. And let's say those are the answers, 5 over 2. Well, this becomes difficult because you're like, all right, I got all these units that are kind of crazy. 1 over seconds for units there, 1 over meters for units there. But take a look. This is in the denominator of the numerator, okay, which means that in the answer, it's going to be in the denominator of the answer unit. Anything in the numerator of the numerator stays up top. So that 1 goes up top there. Anything in the numerator of the denominator goes in the bottom. Anything in the denominator of the denominator goes up top. So what do you end up getting? Meters per second for this one. So if you ever had something where it was 1 over seconds over 1 over meter, it would turn out to be meters per second. How can you check this? What could you do? Instead of dividing these two units, you can multiply by the... So do that. Take a look.
The denominator of the numerator, then it's in the denominator.
Yeah, here's why. Take a look over here. Okay, multiply by the reciprocal. What happens? Meters over second. The 1 is there. The 1 is there. Okay? So this 1 here is really a 1 here. This m in the denominator really bumps up to the numerator portion. Okay? This 1 remains in the numerator. This seconds remains in the denominator. Okay? Now, the other thing you can always remember is time is either seconds, minutes, or hours. And the whole problem dealt with meters per second and meters per second squared and so forth. So it must be seconds. Okay? If the whole problem had been measured in miles per hour and miles per hour squared, then your unit of time would be hours. Okay? Tristan?
Why are we dividing this?
You're not. This was just completely example.
Okay.
That's not. The 5 is just coincidence from the above.
And also, just remind me, there was a question on the homework. It said, what was the least possible amount of time that it could have taken for something to happen?
Forgot to record. Okay? So as I go through the diagram, what is happening? The velocity is doing what from here to here? Increasing. The velocity is increasing. If you have to increase velocity, what must be present? Some form of what? Acceleration. Remember? Acceleration is defined as a change in velocity. So if the velocity is going up, what are you doing in the car? You're hitting the brake or the gas? You're hitting the gas. Now, the velocity is starting to slow down a little bit. The velocity is still increasing, but it's starting to flatline, right? And then around letter B, what do you have? You have a constant velocity, don't you? And then what happens? The velocity starts to? Until it gets down to? So what kind of acceleration do you have from B to C? A decrease or a negative acceleration. Okay, also known as a deceleration. It's not a negative velocity. It's only a negative velocity, Nick, when it goes below the axis line. These are all positives. They're in the first quadrant. So remember that this is really this. Okay? That's what's really going on here. So, let's write this down in words.
It was going backwards, it would be negative. Is that what that is? The negative?
Correct. Okay? In this problem, if you wanted to act this out, you'd be running lightly, then running faster, and then staying at that fast rate for a constant amount of time, then going slower. You're not turning around. You're just slowing down. You're slowing down a little bit. You're slowing down, and then you come to rest. but you're always moving in a positive direction because velocity in this problem is always positive. Okay? Let's write down each section of the graph and what is happening. James first.
Or this could be like a really short jump on the highway for a car. Like accelerates on, stays constant, decelerates up.
Yep, that's a good way to say it. Okay, so from 0 to A, the car or the object accelerates. From 0 to A, the 0 is the origin, to A, the object accelerates because the velocity is increasing. Around point B, say around, meaning around the area of, around point B, there is no acceleration because the velocity is approximately constant. We'll say it is constant, okay, but it's approximately constant there. You can see the flat line at B, so when the velocity doesn't change, there's no acceleration. And then who could fill in the third part for me? Julian.
And from B to C, there's a negative acceleration.
Good.
Or deceleration.
From B to C, there is a negative or deceleration. A negative acceleration or a deceleration. Because the velocity is, everybody? At the end, from B to C, what is happening to the velocity? It's decreasing. It's decreasing. Okay? Now, here's the craziest part of all. What did we do yesterday? Remember? We talked about slope and how the slope of the line was the velocity. Remember yesterday? Now look at the slope. Pick a point at A and draw a tangent line or draw the slope there. Have you all seen tangent lines in geometry? Yes, no, maybe so. How about this? Tell me if this recalls in your memory. A circle with the line that's tangent to it touches only once on the circle like that? Have you seen that? Maybe, maybe not. Okay, make believe you haven't then. We'll assume nobody has, okay? Just for the sake of all of us being on the same wavelength here. Let's assume we haven't seen that before. Now, what a tangent is a line that touches a curve once but never intersects it again. So at point A, if you were to draw a tangent, it would look like this. That's what the tangent line would look like, okay? At point A. What would you say about that line? Is the slope positive, 0, or negative in that line?
Positive.
The slope is positive. What also was positive there? What did we say? Sure, but there was something else we said. Acceleration was positive, wasn't it? Wasn't acceleration positive?
Yeah.
Okay, now go to part B and draw a tangent line. What's the slope of a flat line, everybody?
0.
And what was the acceleration there?
0. No, the same.
The velocity was constant, Luke. I said acceleration, though. Be careful. So, in both cases, the acceleration mimicked what? It was the same as what in both these cases? Yeah, the slope of the tangent line. Let's draw one more at point C. The slope of that tangent line would look something like that, right? And isn't the slope of that green line negative? Isn't it going down? And what did we say about the acceleration there?
Decreasing.
Yeah, be careful, guys. Wrong words. Come on. The acceleration, not the velocity. Thank you. The acceleration is negative. It is not decreasing. The velocity is decreasing. Again, from O to A, the acceleration is positive because the slope is positive, we can say now. At B, the acceleration is 0 because the slope is 0. And at C, the acceleration is negative because the slope is negative. So here's our statement we're going to write. Here's our correlation. The slope of a velocity versus time graph is acceleration. Somebody tell me how that differs from yesterday's statement. How does that differ from the statement we made yesterday about slope and graphs? About slope and graphs. Look back in your other notes. You have them all right on there. Go back to your physics folder, open up 2.1, find out where we made a statement about graphs and slopes and lines. I want you all to be doing this. Let's go. Don't wait for your classmates to do it. We made a general statement about slopes of different kinds of graphs. Not velocity versus time, but we did position versus time yesterday. What was the difference, Nina? Yeah, but now when it's velocity versus time, it is acceleration. So maybe you want to write that to show that they're different. So when the graph is position versus time, the slope is velocity, like we said last unit. But now, when it's velocity versus time, the slope of this is really the acceleration. Okay? That's the difference. It's the acceleration. And notice that it's velocity versus time instead of position versus time. You can always use these graphs to think about logically what is happening, like we did to start. Remember when we started, we said, well, beginning, it's the velocity is increasing. So that must be a positive acceleration. Well, there's the slope. It's positive. Velocity is consistent at B. So there's no acceleration. Well, the slope is 0 again. So you can see how the slope is analogous to the acceleration on this graph. Someone at a hand? Anybody else? Questions on this one? Questions on this? I know it's not easy at first to wrap your head around this. Okay? I'm not asking you that you're going to understand every little bit right away. Okay, but maybe when you're looking at these graphs, writing little words in here might help. You could write in this portion right here, velocity is increasing, so there's positive acceleration. You can write little notes along the way on your graphs. Okay, let's finish today with one more thing here. Let's take a look at one more thing. What I'd like to do is fill in this table. Okay? Let's fill in this table. Now, on the left-hand column, we're going to talk about different types of initial velocity. In the middle column, we'll talk about an acceleration, and then we'll talk about the motion here. Okay, I'm going to fill in the velocity column, and then you're going to have to tell me what goes in the acceleration column. So here, write these as plus, minus, positive, negative, positive, negative. Let's write this as negative or positive. Let's write this as 0. And let's put this as 0. Okay? So let's look at all these scenarios. We have 7 scenarios here. 7 different rows. First, if you have a positive initial velocity, so you're moving in which direction? Right. Agreed? You're moving to the right. How would you speed up? What would your acceleration have to be? What would it have to be? Also positive. Think about it. I'm running this way, but I want to run faster, so I have to push off this way and accelerate to the right. So the acceleration must be positive for that to occur. Now we have a little bit of a tricky part here. Don't jump the gun on your answer. I'm now going in the negative direction. Agreed? That's what negative means for initial velocity. But I want to speed up. I want to get faster in that direction. So which way does my acceleration have to be now? It has to be negative. Let's talk about this. I'm running this way with a certain velocity, but I want to speed up in that direction, which really means get more negative in velocity, right? If I'm already running this way and I want to speed up, now I'm going faster in the negative direction. The only way you can go faster in the negative direction is by having a negative acceleration. An acceleration that pushes you to the left. So this would be a negative symbol. So right away, whenever you want to speed up in general, whether it's that way or that way, you want your velocity and your acceleration to be in the same direction. That's what's showing up here. So that might be your little note you want to write. When you ever have a motion that's speeding up, the velocity and acceleration are acting in the same direction. That's how you speed up. Okay? In a minute, we're going to talk about slowing down. There was a question from, I think,
Yeah.
Nick?
I just
Sorry, I
I
saw a hand.
get how you're dealing with the coordinates of the plane and everything, but when you are going negative and you want it, and you say that you make it more negative acceleration, that will make you go slower.
That would make you go with a higher negative velocity, because you're already going negative. Right? Watch. I'm jogging left,
Yeah.
and now my acceleration is pushing me that way. Aren't I going to go faster that way?
Yeah.
But I'm going faster in the negative direction. It's still called speeding up, but in the negative direction.
Okay.
This is where we're talking about speed and velocity now. Speeding up versus velocity. Okay? Let's talk about the next one that makes sense. Your velocity is to the right. Okay, I'm going this way. Gio, how would you stop me from walking? Which way do you have to push me? If you push me,
Left.
you push me this way, it would push me to the wall, right?
Yeah.
You have to push me to the... So you have to give me an acceleration that way, right? So your acceleration should be negative. And what are you going to get for the next part, you think?
Positive.
So what do you notice now? When you want to slow down, the signs are opposites. And let's go over the next one anyway. So I'm going over this one here with the negative VI we just filled in here. So if I'm moving to the left and I want to slow down, Nick, which way do you have to push me if I'm moving this way to slow me down? Which is in acceleration terms, positive. That's where this positive comes in. In order to slow something down, the acceleration has to be opposite of the velocity. When the acceleration is with the velocity in the same direction, we go back to the first scenario where it was speeding up. Alright. Next. If you have either a negative or a positive velocity, it doesn't matter. How would you maintain that velocity? How would it be constant? What must the acceleration be? Zero. The acceleration has got to be zero for you to maintain a constant velocity. And think logically. If I'm walking like this, constantly, I'm not accelerating. I'm not changing velocity. That only happens when there's zero acceleration. How do you speed up from rest? Speed up from rest. Or, because it's just speeding up. It doesn't matter really in this case. Remember, I'm not saying increasing velocity. If I said increasing velocity, then acceleration must be positive. But if I start at rest, and I start running this way, that's positive acceleration. I'm speeding up to the right. I can start running this way. I'm also speeding up to the left. And that's also speeding up, but in the negative direction. So either way, as long as you have a positive or negative acceleration, you will speed up. And the last thing? Zero, right? Take a look at the last one, make sense of it. How do you remain at rest? By having no acceleration. You don't accelerate. Okay? What? I don't even know what he's saying. Let's stop there. Okay? We'll stop there for today. For the kinematic equations, we're just going to go over the three that exist here. So the first one is just the manipulation of this formula here. If you take this formula and rearrange it and solve for VF, that's what you get there. So that's all that portion is again. Okay, again, a manipulation. So the first equation will be used when we're looking for maybe final velocity, and we have these three, or if we're looking for maybe acceleration, we have these three. But notice the first equation does not have x in it. So this equation has no displacement involved, if you want to write a note. Not using displacement here. The second equation, notice, does have displacement involved in it. It absolutely does. And it has our time and our initial velocity, but it doesn't have final velocity. So this one has no displacement. This one is not used if you're missing the final velocity. And the last one, you'll notice that it's a combination of the first two actually, and it gets rid of time. Right? There's no time in that equation. So if you have every variable but displacement, or if you have almost every variable but displacement and you want to solve for something unknown, you may use this formula. If you know nothing about VF and it's not involved in the problem, you might use this one. If T is not involved anywhere in the problem, you would use this one. But remember that just because you're using X doesn't mean you have to use this problem. If you're trying to find X, but you don't know time, you can't use this here. Maybe you use this one and solve for X and rearrange it, because you don't have time. But these are the three kinematic equations that we're going to use this year to represent motion of an object. Alright, let's take a look at the first example here and decide which of those three kinematic equations we may use. So a race car reaches a speed of 42 meters per second. It then begins a uniform negative acceleration using its parachute and braking system. Comes to rest, keyword comes to rest, in a time period of 5.5 seconds. Find the distance the car traveled during braking. So, let's take a look. It says it reaches a speed of 42, but then comes to rest. So the final velocity is 0 because it comes to rest. Be careful. You might want to think of final velocity as 42 because it says it reaches a speed. Okay, but in this case, it started somewhere else. We don't care where it started. So it reached the speed of 42, then began to brake. So the beginning of the problem is right here. As soon as it reached 42, that's the beginning of the problem. So that's the VI in this problem. Why am I using VI and not speed? Well, because take a look. It's traveling in one direction. It begins a uniform negative acceleration, and it comes to rest. So we know that the acceleration is slowing down the motion. Okay, because it comes to rest, it's acting in the opposite direction. So the time period in this problem is 5.5 seconds. And we want to find the distance traveled, which happens to be the same as the displacement in this problem. But you'll notice we have no way to solve for x right away, simply because the equations that involve x also involve the acceleration. We don't have acceleration. So let's start by finding acceleration. Acceleration is Vf minus Vi, both in meters per second, all over time period. So we really just have negative 42 over the time period of 5.5 seconds. Well, in this problem, it's got to be a negative answer for acceleration, obviously. Well, acceleration turns out to be just negative 7.63 repeating. That's our acceleration we're going to use. So we utilize this formula here, and now we really don't need it anymore once we got the acceleration. So now, given these four variables, let's go ahead and use our new formula. Let's use x equals VIT plus 1/2 AT squared, noticing that we don't need VF anymore because this formula doesn't involve VF. We could have used the third kinematic equation to find x, which does involve VF, but this one is already solved for x, which is what we're looking for. So make it easy on yourself. So I'm just plugging in. Okay, now, key things to note before we go any further. 5.5 is being squared. Square it first, please. Okay, square it first. The quantity on the left-hand side is going to be 231. And now this is going to be actually minus because of this negative that's going on here. This is like a negative portion. Will turn out to be 115.4. Again, using the rounded value of negative 7.63. Now, this is the reason I went over this, or I want to do this. We could look just at the answer here and say, yeah, sure. It's simply just going to give us 115.5. Now, the one thing to note, though, and this is what we're going to really look at, the interest in, is the following. Imagine this problem there had been no deceleration, and the car had just been traveling at a velocity of 42 meters per second, and it maintained it for 5.5 seconds. Well, if there was no acceleration, nothing slowing down the car, no braking system, this part wouldn't exist. This would be 0. So this whole thing would drop off, and you'd be left with just this portion right here, which is 231. So this is how far the car would go at 42 meters per second for 5.5 seconds. But because it was slowing down the whole time in those 5.5 seconds, this is like a negative distance, okay, or a negative displacement, really. In this case, it's canceling out part of the distance that would have been traveled had there been no acceleration. So with the acceleration in this problem, it only went about half as far as it would have. Let's make sure we write our units in meters here. Example 3 says, a plane starting at rest at one end of a runway undergoes a uniform acceleration of 4.8 meters per second squared for 15 seconds before takeoff. What is its speed at takeoff? How long must the runway be for the plane to be able to actually take off? So, we've got starting at rest. Then we've got an acceleration of, and finally we've got a time period of. And this problem is asking us, what is its speed at takeoff? What is its speed at takeoff? So this is the beginning here when it starts at rest. And as it's taking off, that's the end of the problem. So find that. And how long must the runway be? Really means how much ground does this plane need to cover to actually take off. So we're looking for the displacement. So in this problem, it's actually quite simple. We've got these first three pieces of information here. We want to find VF, start with VI plus AT. Well, VF is going to be 0 plus 4.8 meters per second squared times 15 seconds. It's going to give me a final velocity in this problem of 72 meters per second. Now, knowing the final velocity, we could solve for x, the displacement, in different ways. We can go to the third formula now that we know VF, but the third formula is not solved for x, so let's stick with the second formula again. Let's continue to work with the second formula here. Plugging in what we know, this is 0, drops off. Remember, again, to reiterate, square this first, then multiply it by these two quantities. Make sure you PEMDAS it. Square it first. What you're going to end up getting for this portion of the equation is 540 meters. So if you were writing a verbal statement on your test, you would say the speed of the plane at takeoff is 72 meters per second, and the length of the runway must be at least 540 meters for it to actually successfully take off. Where is an application of this? Please, right away, think about aircraft carriers. Planes need to take off all the time from ships, and they only have a certain amount of runway. If they don't successfully, they could, launch off into the water. The final example says a person pushes a stroller from a velocity of 3 meters per second, looks like starting velocity, uniformly accelerating it at a certain rate, acceleration. What is the velocity of the stroller after it has traveled a certain length? So we know initial velocity is 3 meters per second. We know acceleration is a half of a meter per second squared. We also know that it's traveling a certain distance. Well, in this case, since acceleration and velocity are acting in the same direction, we can tell us that 4.75 is actually the displacement. And we're looking for VF. So we know this formula is usable. We know it's usable because we know everything on the right-hand side of the equation here. Okay, again, we know everything on the right-hand side of the equation. Let's go ahead and plug into what we know. Now, plugging in all these quantities, we're going to end up getting the following. Now be careful because your units here are meters squared per second squared. Because again, you squared your units here. This meter and this meter made meters squared over second squared here. Well, the reason you still have squared units is because you have to take the square root at the end. So your final velocity, you get the square root of this whole thing. Remember, it's plus or minus always. Now, it's plus or minus 3.71 meters per second. We'll take a look. It says that the starting velocity was 3, and it accelerated with a positive velocity, so it's got to get faster than 3. So in this case, we have to use the positive root because of that. So again, you'd have the positive root for this one, because it's accelerating it, and it's already started at a positive velocity. Your homework in this section is from 3 different pages.